In this video, I'll be discussing Lewis acids and bases. So a Lewis acid is a compound which accepts an electron pair, and a Lewis base is a compound which donates an electron pair. And sometimes you'll see the phrase electron poor used to describe Lewis acids, and you'll see the term electron rich used to describe Lewis bases. And that's because typically Lewis bases have a surplus of electrons around them, and Lewis acids have a deficit of electrons around them, or they have open slots for electrons. So most of the time what you'll end up seeing is a Lewis base will form a connection with a Lewis acid, and that will give you a new product. So let's look at a few examples of what you'll see acting as a Lewis acid and what you'll see acting as a Lewis base. So here are some common examples of what you'll see acting as Lewis acids. Metal ions. So if you see a metal with a positive charge, something like sodium +1, or iron +3, or any metal with a positive charge, those are going to be acting as Lewis acids. And we see these especially when we look at coordination complexes. H+. So H+ is a very common Lewis acid. Boron and aluminum compounds. So if you see a compound like BF3 or AlCl3 or AlF3 or any of those compounds where boron or aluminum are the central atom, those are going to be very common Lewis acids, especially BF3. You see BF3 a lot acting as a Lewis acid. And lastly here we'll look at carbocations. So if you're not familiar with the term carbocation, this simply refers to a positively charged carbon. And we're going to see this especially when we look at nucleophilic substitution reactions, which is a special type of Lewis acid-base reaction. But carbocation simply means a positively charged carbon, and we're going to see that acting as a Lewis acid. These aren't the entirety of the Lewis acids that you'll see. There's definitely ones that aren't some of these, but these are just some very common examples that you see come up a lot. So here are some common examples of what you'll see acting as Lewis bases. So halides are very often going to be Lewis bases. So halides are just the negative ions of the halogens. So fluoride, chloride, etc. Oxygen. Now, when you see oxygen in certain compounds where it has a lot of lone pairs around it, that's most likely going to be acting as a Lewis base. So, for example, hydroxide, which is this OH-1, water, sulfate ions, nitrate ions. You're going to see these oxygen compounds acting as Lewis bases. Nitrogen compounds are very common Lewis bases. And that's because nitrogen likes to have a lone pair on it most of the time for charge purposes, for formal charge purposes. So because nitrogen likes to have a lone pair on it, it's very often going to be a Lewis base. So NH3, NH2-1, etc., nitrogen likes to act as a Lewis base. Same thing goes for phosphorus, because phosphorus has a similar look to nitrogen, and that phosphorus also likes to have a lone pair on it most of the time. So compounds like PH3, PF3, etc., those are going to be commonly seen as Lewis bases. And in general, Lewis bases are going to be compounds with a lot of electrons. So look for elements or atoms with a lot of lone pairs around them. If they have a lot of lone pairs around them, especially if it's the central atom, that compound is most likely going to be acting as a Lewis base. So look for lone pairs, particularly on the central atom, if you want to see if something is a Lewis base or not. Lewis acids tend to be metals, and they tend to be positively charged. So if something has a positive charge, it's more likely to be a Lewis acid. If something has a negative charge, it's more likely to be a Lewis base in general. So now let's look at a few examples of these Lewis acid-base reactions taking place. So here is a nice simple example of a Lewis acid-base reaction. So here we have ammonia reacting with a hydrogen ion, and it's going to produce the compound ammonium. So what you'll see here is we have the NH3, which we know is going to act as a Lewis base because of the lone pair on the nitrogen, and the H plus is going to act as a Lewis acid since it's that positively charged ion. So it might actually help to draw out the Lewis structures of, well, the Lewis structure of NH3 at least, to see what's actually occurring in this reaction. So if we look at the Lewis structures here, you'll see that this nitrogen in our ammonia molecule has this lone pair on top of it. And remember, this ammonia is acting as our Lewis base. So this electron pair on the nitrogen is going to be picked up by this H plus. And what ends up happening is a new bond forms between the nitrogen and the hydrogen based on the fact that this lone pair picks up the hydrogen, and that new bond is formed. And we end up with this product here, which is our NH4 plus. And this product has a special name. There's a special term that we call this adduct. So adduct is the term that we use for this product of a Lewis acid-base reaction, where the acid and the base are kind of smushed together and they form a new bond between the two of them. And this is called the adduct, although sometimes you'll also see it referred to as the acid-base adduct. But either way, it's called adduct. So here's another little example of one of these Lewis acid-base reactions. So here we have BF3, which is going to be our Lewis acid, Cn- cyanide, which is going to be our Lewis base, and from that we get our adduct, which is this BF3CN complex. And based on the Lewis structures, you can see that this lone pair on the carbon is going to get sucked in, or is going to suck in the boron, right? And from that, a new connection is going to be made between the boron and the carbon, and this is going to give you your acid-base adduct for this reaction. And this would be our new product that we form, the adduct. So in a separate video, we'll look at coordination complexes and nucleophilic substitution. But for right now, this is just sort of the basics behind Lewis acids and bases.